And greetings, friends. Here we are for lab number, well, this is lab during week 6, so I call it lab 6. We're going to take out a little bit more diffraction this week, so we got a couple of activities which are real cool, and hopefully you'll have a bit of fun. A lot of this lab is predicated on a statement that I made in the lab write-up, which is that a pattern that develops from the single slit, as we've been studying, or the double slit, is identical to a pattern in which, instead of having the slit and a blocking, something that blocks all around it, right? What if you took the thing that made the slit and put that in the way of the beam and then threw everything else away? So for example, if you thought of taking a piece of paper and then making a small little cut, so you had this really thin piece of paper, if you shine the laser through the slit that you just made, you'll get a pattern. If you throw away the paper and you take this tiny little ribbon and you put that in the way, you should get the same pattern, okay? Because the thickness of that object and the width of the slit are exactly the same. So as long as that's true, you'll get the same pattern, all right? So we're going to explore that and take advantage of that this week. But first, we're going to start by doing something similar to what we did last time, which is to see if we can look at a pattern of the laser light as it passes through a slit, in this case the single slit, and see if we can calculate what the laser wavelength is. So for that, we're going to do a diffraction grading first. Sorry, we're doing the single slit to predict the slit widths. We're going to do the diffraction grading first. So for this activity, we need the diffraction grading, which has the rainbow pattern on it. And you'll need your laser. And what I did was I just took the box and a book, and I have just made it such that once I have the laser set up at the right height on top of the book, okay, so I have a book like this, and I have the laser just mounted on there like this. Oh, there we go. Okay, like this, so that when I move it back just a little bit, I'm going to balance the objects that we're going to use. I'm going to balance them right in front of this, and I've just put that entire setup on top of the lab box that you have for your kit. And so when I have the laser shining and I have my diffraction grading, it says here I've got 1,000 lines per millimeter, okay? And so when I take that and I'm going to put it in front of my laser, right? My laser is going to be shining. I'm going to set this down in front of it like so, and I'm going to have the light going through. There's going to be maxima projected onto the wall or the screen, whatever you're looking at. And depending on how far away you are from grating to wall, you may or may not be able to get both first order maxima on the screen or the wall. If you can, then when you do your measurement, please feel free to measure from the first maximum on one side past the central maximum over to the maximum on the other side, and then divide by 2. It kind of helps reduce uncertainty. If you cannot do that, then I would suggest trying to get one pattern on the wall, measuring that, and then scooting it over, so right, just kind of scooting it, so rotating it so that it gets the other pattern on the wall. I get the central maximum to the first maximum. I measure that distance, I scoot it around, I get central maximum to first maximum. I take those 2 measurements and I can take the average of those. Using that, then we're going to use the diffraction grading locator, fringe locator, which was exactly the same as the double slit. In other words, it's d sine theta equal to m lambda. I only could get the first order on the screen. If you have room to get to the second order, great, do it. If there's more that you can do, great, go ahead and do it. I could only hit the first maximum, so my d sine theta was just equal to 1 lambda. And then d we know from the 1,000 millimeters, 1,000 lines per millimeter, okay? And the sine of theta, we will have to calculate the theta via the inverse tangent of the distance and the slit screen. Distance from central maximum to first maximum, and then distance from screen to grating. Remember, the small angle approximation is not always valid in the diffraction grating case. So I recommend, just for practice's sake, go ahead, calculate the tangent, right? Y divided by D. Find the inverse tangent, use that angle, put it in the sine. It may come out to be fairly like, oh, why did I bother doing all that? Partly just for practice's sake, just to get you into the mindset of, hey, there may be times when this is not going to work as a small angle approximation. So my suggestion would be, don't get in the habit of thinking small angles when you're using gratings, right? It's fine for the double slit and the single slit, but gratings, the issue is it may not be, right? All right, so your goal there is to back off the wavelength of the laser and compare it to what we had last week. What did you find last week from when you did the double slit experiment and the measurements, and you found the wavelength of this thing? Compare, okay? If you feel like you've got one that's more of a true representation, you feel like, hey, I did better using the experimental techniques to get this number and it feels better than that number, then great, by all means use that one. In the absence of that, if you'd like to take an average of the two, that's great. What you want to have is the situation where they are somewhat reasonably close to each other, rather than being one is saying 200 and one saying 4,500, right? So you want them both. This is red, so you know it's in the 600s. It's probably in the 630s somewhere. That's where mine came out to be. So it might be somewhere between 630 to 650. All right, or it may be between 600 and 650. Say that's probably a better range for you to shoot for. So you'll have that. Okay, so that'll be the first task, is to do measurements with the grating, back off the wavelength, and compare it to what we had in the previous lab. All right, so that's the end of this. Oh, by the way, do have some fun looking through this. You should find rainbows. It's a lot of fun to just kind of look through these things. And the warning that you should not look directly into the sun is basically true at all points during your life. So if you need to remember that, maybe carry this with you. Unless you're wearing a welding helmet, in which case, well, you would have to have the mask down, and then you could look directly at the sun. All right, so that's first part. Part two here is going to be on the single slit. So we're going to go back to the comb, and just like we did last time, I'm going to ask you to try and isolate one piece of the comb. Now, instead of two slits, we're going to only do one slit this time. But here's what I found that was much better in this case. It's just very fiddly, and probably this is the most problematic piece of doing this lab, is trying to get just the single slit. But what I found worked the best, instead of trying to get two of them close together like this, I found that if I used the very edge, right, and then I covered everything up to there, I could get the one single slit at the very end. And so I did that on both, right? And it's really useful because the tape or a cardstock or something will have a pretty nice straight edge. And I was having trouble getting it to a single slit just in the middle here, because one wouldn't quite be exactly right, and then there would be a little light coming through the bottom, and then this one was, and then now I'm like this, and the slit width is changing as it goes up and down. Guys, I'm exaggerating the sizes of these things, but it was a little bit aggravating. So I'm trying to cut all that out for you, trying to just get you skating over to what I think is the easiest solution. Just use the edge, and then I taped all the way out. Make sure that you are totally covering everything else, though, okay? And that your tape is totally obscuring everything past the finger, and you've got just the single slit. So what we're going to do now is try to figure out what that slit size is. What's the slit width? And then we're going to flip it over, do the same thing on the small side. All right, so the comb has those two spacings. Excuse me, and we're just going to try and figure out what each one of them is. And when we figure that out, of course, we then can measure it just like we did last week with the double slit by putting the tape measure straight down on the side and then counting the fringes or counting the fingers on the comb and looking at the measurements on the tape measure. Okay, so that will be the comparison by which we can figure out whether or not our diffraction calculations are going to be somewhere in the ballpark. All right, but same basic idea. I had my box and my lab kit box and my book with the laser on it. So all I'm going to do is put this down in front of the whole thing, and you can't really see what I got going on here. So let me see if I can just move it over here for you. Taped the laser down. So I've got my laser. Here it is right here. I've got my illustrated guide to poultry breeds, that's pretty handy. And then I'm just going to be able to pop this thing down on the top of that, and it's going to shine through this one. I'm going to turn it over, shine it through the other side, right? And then I'll be able to take those measurements on the screen. So same basic principle as it was for the grading. Count off your diffraction minima. I usually tend to go for the minima because they're smaller, and so I can at least feel like I have a better shot at measuring where the minimum actually is versus going into one of these large central maxes and trying to say, well, this is the middle. So at least with the minima, I can say, oh, this is the edge of the minima. Then I can just go edge to edge, right? If I use the same edge, I go from the left side of this minima to the left side of this minima across the central maximum. Then I can use the larger distance of the measurement of y, divide it by 2, and that'll reduce my uncertainty somewhat. Okay, so the goal here is to try and find the slit width of the comb spacings on either side of the comb, and then compare with basically what turns out to be a direct measurement of those. Okay, so that is part 2. And now we reach part 3, and we say, well, this is the situation where the obstacle starts coming into play, right? We haven't used that to this point, but now this is where we're gonna start using that. So in the lab, I said measuring the diameter or thickness of a human hair. Now, this means you have to procure by hook or by crook some type of hair. Now, I did say human. I'm not picky. If you have a fairly chill cat, I'm sure it wouldn't mind. Probably some of the tail hair. Were you to have a dog, which happened to have some shagginess to it. My hound, for example, I think you could probably run your hand through her fur coat and come up with a nice clump, and she wouldn't even notice. So that's you could totally do that. If you have hair that is not like mine, then maybe you've got a chance of getting one of those. If you have none of those options, perhaps a piece of thread, small gauge wire, if you have the bristles from a paintbrush or something like that, you are free to be somewhat creative with this should you need to be. All right. Try to make it something interesting where you wouldn't necessarily be able to say, aha, I already know the answer to this. Now in the lab, I did say in order to have something to compare to, right, which is the heart of experimental science, I said look up online what would be approximately a diameter of a hair and see if that range, they will probably give you a range and see if your value is somewhere within there, or really the opposite, see if that range lies or contains your value. So, and by the way, try to find a fractional uncertainty when you go through and do your measurements for this. So the measurements for the hair will be exactly the same as it was for the slit in part 2. Okay, you're going to put the hair down. What I did was I have a roll of tape. So what I did was I just taped the hair right across the front here. You could use anything like, if you had a paper cup that you could cut the bottom off, or you have like even a pair of scissors, right? You can just thread it across the handle of the scissors. Anything like that will work. And you put it in front of the laser, right? And then the laser is going to shine onto it, and it's going to project a pattern on the wall or screen that is going to be very similar to a single slit pattern. So the measurements that we're going to do are basically exactly the same as they would be in the single slit part on number 2. I again suggest measuring from one side of the central maximum over to the other side of the central maximum and dividing by 2. Make sure to count your minima as best you can so you don't have any uncertainty in that. When you come to calculating the uncertainty in the width of the hair, I would recommend thinking about your uncertainty in the, like I said, the measurement across the central maximum that we just did. That's probably where most of your uncertainty is going to come from. With the tape measure that we gave you, you'll be able to see, I've got, it does mark millimeters on there, and so you might have a plus or minus a millimeter, possibly 2, depending on if you're like me and I'm not entirely sure. So your fractional uncertainty is the value that you measure, right? Which is really, I guess it's really half that value, because that's the part you're going to use to do the calculation. It's half that value, right? And you're going to use that uncertainty. So divide the uncertainty by the value. That's your fractional uncertainty. You can check to make sure that it is actually the most uncertain thing, because I'm hoping you don't have any uncertainty in the counting of the fringes, right? Because if you're thinking about how to do this, your sine theta would turn into approximately y over d, and we're calculating a. So we have y, we have d, and we have m. So if you have uncertainty in your m value, you might be plus or minus 1 on that. I think if you just count them, you should have no uncertainty in that. It should just be a number. The d value is distance from hair to screen. And again, that would be measured by a ruler or something like that, where you could say, well, it might be about a millimeter or 2, possibly a centimeter. But I would venture to say that your uncertainty, the fractional uncertainty in the distance from the hair to the screen, is going to be much less than the fractional uncertainty in the y distance. Okay, so use the y distance, delta y over y, and set that equal to delta a over a, and that's how you can get in the lab. I wrote sigma predicted or something like that. So sigma experimental. Maybe it's nothing, but anyways, point being, that's how you can calculate approximately what the uncertainty in the hair diameter is. Okay. If you set those two fractionals equal to each other and then solve for the delta in A, then you're going to have it. And I said to use twice that value to give you a 95% confidence level. Compare that to some way of possibly measuring what it is that you have, what you have. So, or find some value to compare. Really, that's what I want you to try and do is we don't want to do these measurements just in a vacuum. We want to actually see, hey, right, what do we got? Are we in the ballpark here? Are we working right? So if you have thin gauge thread or wire, possibly you'll know if it's a gauge of a wire. Then you can look up the gauge and what its diameter is. Threads, again, try to find something that you can compare to. All right. Okay, so that would be part 3, thickness of the hair. And then the last part is a little bit of fun games. You should have a square, a white square of cheesecloth, and you can see this is opaque. You can still see me through this. However, it is made of something. It's not just completely devoid of material in here. So the question is, what kind of structure is this? Because I certainly cannot see just by looking here. Is it made of squares, or how? You're right. Like how fine is this? Yeah, I can't really even see the structure of it just by looking. So again, same setup. We're going to take this. I'm going to tape it onto something. I used the roll of tape again, just like this, and I just taped it flat, and I put it in front of the laser, and the laser shines through it, and you get this really cool looking pattern on the wall. And that really cool pattern on the wall is going to have double slit pattern in it and a single slit pattern in it. And guess what we get to do? Use both of the patterns. We're going to make measurements of both the interference fringes. So if you look very closely, you'll be able to see that there's a bunch of little tiny bright and dark fringes right inside, right around the central maximum from the diffraction. And then you'll see a larger minimum, and there's your diffraction minimum. Okay, so same basic idea as before. We're going to measure fringes. Again, I would measure across the central maximum from one side to the other. I chose to measure the entire central maximum, the entire central diffraction maximum, in which I counted a certain number of interference fringes. So I measured across that, and I said, okay, bright fringe to bright fringe, or actually it was dark fringe to dark fringe, because I found that the maxima of one lay right in the diffraction minimum space. So that was kind of cool. What are ultimately these numbers going to give us? Well, we are going to measure the y distances, measure the d distances, and solve, once again, using our laser wavelength that we found in part one. We're going to solve for the a, which is the slit width, effectively, and the d, which is the slit spacing, again, effectively. So what do those numbers mean in this case, right? It means things like how thick is the material that they made this cheesecloth out of, right? That would be one thing. And right, so how big of spacing is there between? So it kind of gives you information about both the thickness of the material and the spaces between the material, right? So have a bit of fun with that. See if you can come up with an A value and a D value for the cheesecloth, and see if it seems to be in the ballpark of approximately what you think seems reasonable. Here is some situation where having just gotten through saying I want something to compare to, it could be kind of difficult to find something to compare this to, but if you track something down, I didn't find anything very obvious about this. If I could find anything about the size of the material and the construction of this stuff, I didn't find anything that was particularly compelling that I felt good about measuring. So having just gotten through ranting about how important it is to compare with things, I don't know if there's really a good comparison for this one, but the good news is that having done the comparisons for the last three parts, if you're coming out within the ballpark, hopefully that gives you confidence to go and take a measurement of this and see if you can find out what this looks like. All right, what kind of numbers we're going to get from this. So that is more or less what we have going on this week. All right, so part one, the diffraction grading and finding the wavelength of the laser. Part two, the slits, trying to use the wavelength that we have to calculate what the slit values are, what the slit widths are on both sides of the comb. Part three is the using a hair, and part four is cheesecloth. Alrighty. So in the cases of 2, 3, and 4, right, we are really trying to find out something about the structure and spacing of the materials. Right, we're trying to find out or thickness if it's the hair. Right, how thick are the not how thick, how spaced apart are the fingers? How thick is the hair? What does the structure of this look like? And we're doing it all from an analysis of diffraction patterns. So take some care, especially with the construction of the single slit. This was the part where I had the most trouble, I think, in this lab, and it really helped me to just have a non-laser light source behind here, so I could just make sure that when I put the tape on here, there was no leakage of light from the neighboring space slit, right? So I know that I covered all that as best I could, and that it's pretty straight, etc., etc. So using that as a guide is pretty helpful. Just by way of our safety warning this week, obviously we are still using the laser, so just please be aware of shining it where people are potentially, I guess I should say, be aware of not shining it where people are potentially walking. When you are using the diffraction grading, also please be prepared for there to be a reflection. Okay, so if there's if you're looking at it from this side, shining the laser in, just be aware that it could bounce off. It will bounce off, and you'll get a reflection off it. Or just be aware that if there's someone behind this, that they are aware of that. Other than that, I think it's a pretty. I mean, I kind of enjoy these fun, like, try to figure out what's going on. What's the spacing? Can I figure that out? And then what's going on with this thing? It's kind of fun to have a little bit of a challenge to figure out what does this look like, and how fine is the spacing, and how fine is the thread that they're using, and that kind of thing. It's a bit of fun. So ultimately, yeah, that's what I've got, and I hope you enjoy a sunny and wonderful weekend. It looks like we're going to have pretty good weather out there, so have fun at the lab, have fun outside the lab, and just, I guess that means you'll have fun in general. So wonderful. Have a great weekend, and I will talk to you on Tuesday, where we pick up with our thermo. So great. Happy weekend, everybody. Talk to you next time.